Right, good morning everybody. My name's Robert and I've got an interesting machining process that I would like to show you about. It's certainly nothing top secret, but with the decline of manufacturing here in Australia, a lot of you may never have seen it and may not have the opportunity to do it. But here I am to do it. What I want to show you is how to cut a helical groove on this brass shaft. It's 1.5 inch diameter brass. There are 20 flutes in it, and they're formed with a 4mm ball end slot drill. Throughout this demonstration, I will be going from inches to millimetres because I'm quite comfortable using both, and that's what we do. I don't write a hard and fast rule on inches or millimetres. It's just whatever is easier to do the job. The machine I'll be doing it on is behind me, the Pacific turret mill, one that I bought second hand about 8 years ago, and it's a very robust machine. On another market it would be called a Lagoon, but here in Australia they were called a Pacific, and it's a very good machine. It's graduated in inches, all the dials, and the table, the longitudinal travel of the table is about 650 millimetres, but with one turn of the screw it's 5 threads to the inch. So 200th hour progression on the table. I'm fortunate enough to have 2 milling machines. I also have a Bridgeport that I bought new in 1980, but it is graduated in metric measurements. The lead screw is 5mm, and the table travel is very similar to this Pacific, but I prefer to do this job on the Pacific milling machine. It's fitted with a you see here it's an automatic travel attachment that goes forward or reverse, and variable speed by moving this I suppose it's like a Norton box on a lathe. Just need to give it a bit of a nudge. Must be a bit of stage fright. Right, that's where it is. I'll demonstrate that for you without actually doing anything. I've started the motor. Then if I want it to travel in the left-hand direction, I flick the lever that way and away she goes. It'll go until as far as the stop is set, or until I decide to, and that's always a bit tricky to do that. Unfortunately, I've never been able to work out if it has a rapid travel on that machine. So if there's someone out there in the whole wide world that's watching this and they know how I can rapid traverse it, please let me know, because I don't know. I've tried all sorts of things and haven't had any success. On the Bridgeport, it's quite easily done, but I'm not doing this job on the Bridgeport. I'm doing it on the Pacific. The job on hand, as I said before, is 20 flutes of 4mm diameter on ball end slot drill, and this job here is scrap. I did it a few years ago, that's why it doesn't look very shiny. And it has a pitch of around about or lead rather, of 48 inches. on a full turn. This one is around about 16 inches or 400 millimetres. And how do we do that? So I've never done this before, so I'm all at sea. When I bought the Bridgeport, I also bought the dividing head, which we can look at later, and with it came this book by the manufacturers of the dividing head. It's a Spanish thing, seems to be very good quality. I've never had any bother with it, and I've used it a lot. I've been making these fluted shafts for over 20 years, but I'm just about ready to throw the pin in, so I thought I'd let the world know how they're done. To find the lead, you can work it out mathematically if you're so clever, but believe me, it's a bit of a tricky process. The easiest way I found is to look it up in this book. I'll just grab one at random. I'll put this ruler across there. Okay. If I had a pitch or lead of 44 inches on this machine, which is 5 threads per inch, we look over in this column, we have a gear train, a 40, a 24, a 64 and another 24. And it just depends where you put them on the gear train as to what they do. If you could put the right gears in the wrong position, you won't get the right answer. If, for example, I wanted a lead of 45 inches on that job, no matter how many teeth are in it, or flutes, I can work out the gearing with a complicated formula, which is not difficult, but why do it if it's already written out for you? We would need, for this machine, which is 5 threads per inch, a 40, a 24, a 54 and another 24 gear. And the gears come with the machine when you buy them, or if you've got one second hand, you never seem to get the gears with it, you can always make them. And there's a list of gears that you require up here. These are the gears that are available with the machine. A 24 or two 24s, a 28, a 32, a 40, a 44, a 48, 56, 64, 72, 86 and 100 teeth. And with that combination, I guess a clever man a long time ago has worked out that's all the gears you need to get any combination of pitches. Whether it be the flutes on a drill or a reamer, or the angle on a camshaft gear on your car, or any helical gear, you can get it with these, I believe. If you can't, well, you get it pretty close and it doesn't matter. As I've explained before, we're using a 4mm ball end slot drill. High-speed steel, and I've got it mounted in a ER16 chuck for clarity, because it's all open and we can see what we're doing. There are a multitude of chucks you can use, but I choose this one because for the purposes of this viewing, we can see what we're doing. It is an International 40 taper on the spindle, which is opposed to the Bridgeport, which has the standard R8 spindle, which is a bit of a nuisance because it means I've had to double up on tooling for chucks and for boring heads and for anything like that. So nothing like having twice the expense. That means you halve your profit, but it makes it all fun and dandy. And I'll be using the depth stop on the job. I've got it set to depth, so when I bring it against this stop here, it's cutting to the correct depth when I start to do the job. But we'll just get that out of the way for the moment. This machine has a travel on the table of about 650 millimetres, and the job requires a 600 millimetre flute, which is getting pretty close to its capacity. The dividing head, as such, takes up room. I suppose it would be 300 mil, maybe a little more, or a foot, and then the tailstock has to be bolted somewhere too. So to overcome the problem, because we're really working on its extremities, I've made up a bit of a fixture which started out life just as a piece of scrap steel, and I bolted it to the table. Well, I had the scraps, it's not just scrap steel, I had it surface ground, flat and parallel, 2 pieces. This piece here bolts to the table, then the dividing head bolts to it. Height is immaterial, but it's around about, I don't know, 28 millimetres, I guess it was to start with. And then down on the tailstock end, I've got a similar piece of steel that I can loosen these 4 bolts. It will slide in and out concertina fashion, much the same as a capstan lathe does. To get a longer stroke. I have to do that because if you look at the tailstock, it's out over this drainage groove in the table, and for that front bolt, which you may not see on this shot, but the rear one is out over fresh air. Now I would have very good and extreme difficulty bolting that tailstock to nothing. So to overcome the problem, and it is a problem with milling machines, the table is always too short to do a long job. So that's something that maybe you could keep in mind if you ever need to extend the capacity within reasonable limits. But I've found it works very well, and I do have varying lengths of these rods, so I just adjust this fixture thing in or out depending on the job. Now this dividing head, pretty much common to all dividing heads, is a 40:1 ratio. That means one turn on this crank here will move that spindle there 1/40th of a turn, which I can demonstrate. That 1, 2. 2 turns will give me 20 equal spaces on the job. Now that's all very well if we're doing a straight flute. We just go backwards and forwards and we'll cut 20 flutes, no problem. But remember, we're cutting a helix, or 20 helixes. So that's where this comes into play. It's what they call a universal dividing head, and it's got all these knobs and gears and things on it that are attached to the spindle or the lead screw of the machine down here, which I've said before is 5 threads per inch. And the trick is to get, as we traverse along on the travel of the machine, we need to get an even rotation on the job, which is achieved by this dividing head. I can demonstrate that quite simply. Again, I'll just switch on the power and Dennis will show what happens to the gears and the spindle. Always keep clear of the gears because they will grab and make mincemeat out of you. But you can see the chuck is slowly rotating, and if we leave it going long enough, it will give us a full turn if we had the travel on the machine. What, that it? You'll also notice this index plate here is rotating as you go. This is just an end shot of the compound gear train to see how it works. If you look on the, I won't put my fingers near it, but that gear there, you can see it's totally encased by this plate and the bigger gear. That was the spindle I had to make to do that job. There was no way I could use the standard spindles to get the assembly, so it's just a thing I had to do to make it work. Now, because of the fact that the dividing head takes up a bit of room and we've got limited travel, I've had to offset the turret a little bit. I don't know what it is in degrees, but if we were to drop a line down through the spindle, it would about line up with the edge of the knee here. That's so that everything has got room to operate. And with a ball end cutter, it doesn't matter. We don't alter any profiles or anything like that. I've already centred the job up and set the position of the piece of brass into the correct stops and everything, so we're just about ready to go. So with your permission and your anxiety, we should have a word from our sponsors at this stage, just to keep us on tenterhooks. I think we're ready to go now. I've put a couple of pieces of cardboard on the table here to catch the scrap because, believe it or not, there's a fair bit of brass comes off this, and I've never been one to waste material if we can get away with it. So this machine here is pretty rowdy, so I don't know what Dennis is going to do with the sound recording when I put the spindle on. But what I'll do, I'll start the spindle, I'll bring the quill down, set it to a stop, and then engage the travel on the machine, and we'll see what happens. That's the table motor set in action. Just make sure it's fully back against the stop. Engage the cutter, and away we go. I do the job dry because, for one thing, soluble oil makes a hell of a mess, and I've been doing these things for so long, I get a good life out of the cutter. I use Australian-made cutters because I've found them superior to the imported ones. They might be a little bit dearer, but far superior. The ones I like to use are Capital Cutting Tools. They're available from the manufacturers in Hamilton, Victoria. I've got no ties with them, but if you want cutters, high-speed steel cutters, give them a call and I'm sure they'll be glad to help you. Now, as you can see, we've got here a groove. This is the part that I don't like. I wind the table back by hand. As I said before, if someone knows how to do a rapid traverse, please let me know because I'll be very grateful. But I think it's 117 revolutions I have to do, and at the end of 20 it gets pretty tiring. These job, they're used in pairs, a left hand and a right hand direction of rotation. Whatever the one I did last, because I only use this dividing head for this job, I do that. That's the first one, and then when I do the second one or whatever the second batch is, I just change the gears with the idler gears to change the direction of rotation. Everything else remains the same, but the spindle will rotate in the opposite direction. But just so we don't think that I did something magical and mystical, I'll show you how simple it is to do the second tooth and subsequent ones. We won't do the whole lot because we don't have that much time, but you'll get the general idea of how it's done. To index for the next flute, I have to withdraw this pin out of this index plate and then I can rotate it. But just in case of any vibration that may have occurred, I always like to make sure that that pin is against the clock face. So I'll pull it out, put it in a place where it won't go back, and then go 2 revolutions. 1, 2. Make sure the pin is in the hole, seated firmly. That has rotated the correct angle, and we can do it all again. I'll just wind that back along so you can get a better shot of the 2 grooves that I've cut. And you can see the angle that they've formed. So I do that another 18 times and that job's complete. Then I'll hit it with a bit of sandpaper just to polish off any burrs and make it look. So there are 2 of the grooves completed, another 18 to go, which I'm not going to bore you with because it's getting on for lunchtime. But the next one that I do, I'll change the rotation by the addition of or removing one of the gears in the gear train, and that'll change the direction of rotation. Everything else will be the same. But I hope that you've found that interesting. I've enjoyed doing this production, and I've been doing these things for over 20 years now. I don't know how many I've done, but I'm just about to retire, and I don't know what the poor bloke that had them or I make them for is going to do, because no one else seems to know how to do this. But it's quite simple if you have the right gear. You don't need computerised equipment. This is something that's probably 19th century designs, bought in the 20th century, and here we are in the 21st century and it's still doing a very good job.